Thanks for having me. So today I want to talk to you about, as Marcel said, 21 centimeter cosmology, but a particular brand of it. High redshift 21 centimeter cosmology to probe the epoch of first stars and galaxies, cosmic dawn, as we kind of loosely call it. And a lot of the times I'm going to anchor this discussion on the hydrogen epoch of reionization array, HERA. That's a collaboration that I'm involved with. I'll talk a little bit about things like a little bit of hardware, some analysis effort, and also show you some results from the field that that we've put out so far. Now I picked this title slide because I think it's a nice representation of where we are right now as a community. So this is a picture of the South African Karoo Desert, where we build our instruments. And what you're seeing is a field in transition, okay? In the background here, you see the paper array, those antennas for the kind of previous generation of instruments. And I'll talk a little bit, very briefly, about results that came out of such instruments. But what's really exciting here that we're looking forward to is that we're now building HERA, this next, I guess now current generation instrument that we think is really going to open up cosmic dawn to 21 centimeter observations. But first, let's step back and talk about the big picture. You know, what's the vision here? So suppose I were to draw a picture of our observable universe, to scale, co-moving coordinates, us in the middle here, looking out towards higher and higher redshifts. And we can ask how much of this observable volume have we actually observed? Have we actually systematically mapped out in a high precision, high signal to noise way? I've colored that in here, right? We've got traditional galaxy surveys right here, and modern galaxy surveys and quasar surveys extending out a little bit. And of course, at high redshifts, we've got the cosmic microwave background as well. And what this doesn't include, of course, are individual objects here and there, a lot of which are extremely interesting. But in terms of a systematic mapping, there's a lot that has yet to be covered. We want to change that with 21 centimeter cosmology. We want to use the fact that hydrogen is everywhere in the universe, so therefore it can act as a tracer of structure and astrophysics to make large-scale maps. And luckily for us, of course, quantum mechanics tells us there is a way to see hydrogens, the 21 centimeter transition. It can absorb or emit 21 centimeter photons and use that to map out our universe. And since you know that the 21 centimeter line has a rest wavelength of, well, 21 centimeters, by measuring the redshift or observed frequency, we actually have 3D information. We have a line of sight radial distance, and in principle, we can map out huge 3D volumes of our universe. Now, this is a pretty ambitious thing, so just to lower our ambitions a little bit for the next 10 years or so, a lot of us are focused on just this yellow ring here, which roughly corresponds to the redshifts where we think the epoch of reionization occurred. And so just to orient ourselves a little bit, here's a cosmic timeline. It's a function of redshift going down this way. You start off after recombination with hydrogen atoms and other matter slowly clumping together and together, eventually getting to the point where you can ignite the first stars and galaxies, ending what we call the dark ages. And when these first galaxies build up enough UV luminosity to ionize the hydrogen in the intergalactic medium between galaxies, they actually push our universe through a pretty big transition where the IgM goes from almost all neutral to almost all ionized, and we call that reionization. And this is a really interesting epoch, mostly because we know very little about it. We have theoretical simulations, like these ones right here. This is done by Marcelo Alvarez. What you're seeing here are basically first galaxies producing UV photons from a lot of star formation, and eventually these photons escaping out into the IGM, ionizing the regions around them, so that those are these blue bubbles. And as time goes on, you ionize more and more, the bubbles get larger and larger, eventually they coalesce and basically connect up, fill the entire volume, and we say our universe is reionized. So this is a movie. We haven't observed anything like this, but we'd like to. So eventually we'd like to make 3D maps like this, two angles in the sky, and then again the frequency or the redshift direction gives us our depth. So you see here, we're going to be sensitive to things like the density of hydrogen. Darker red parts are the parts that have a little bit more dense hydrogen, and therefore a slightly stronger signal. White regions are these ionized bubbles where the hydrogen is ionized, so there isn't any signal for us to see. So in a little bit more detail, we're basically using the CMB as a backlight for this hydrogen. So we are measuring a brightness temperature contrast as a result of having this hydrogen absorbing or emitting photons. So this brightness temperature contrast, the signal we see, as you can imagine, is proportional to the density of stuff. More stuff, bigger signal. It's proportional to XH1, the neutral fraction of the hydrogen. This goes from 0 to 1. 1 means it's all neutral. 0 means it's all ionized, and therefore no signal again. And it also depends on this complicated function of temperatures. Depends on the CMB temperature because we're using the CMB as a backlight, but it also has a spin temperature here, which quantifies the relative number of hydrogen atoms in the ground versus the excited hyperfine state. If most of the hydrogen atoms are in the ground hyperfine state, then you're likely to get absorption, and you see this number becomes negative to reflect that. Whereas if you've got most of your hydrogen, say, in the excited state, you're most likely to get emission, and this is going to be positive. So the point here is that we are sensitive to a lot of the right astrophysics here. If we're trying to probe reionization, of course, it's nice that we are going to be sensitive to the neutral fraction. The spin temperature, too, depends on the details of the environment that the hydrogen finds itself in. At certain epochs, for example, this is going to be coupled to the gas temperature of the hydrogen, so that's telling you something about the temperature, the kinetic temperature of the hydrogen, but also to other contributions like the UV flux and so on. So this is a nice way for us to directly measure the epoch of reionization, and that's really crucial, just because we know so little about it. So to give you a sense for our ignorance, if I tell you that our universe went from all neutral to all ionized, probably the most basic thing you might ask for is, how did that happen as a function of time? How did the neutral fraction evolve as a function of redshift? All right? We really don't know. This is a nice Bayesian combination done by Grieg and Messenger based on a whole bunch of, basically a grab bag of a whole bunch of different constraints, including things like Lyman alpha forest, some quasar constraints, CMB, and so on. And you can see this 95% confidence region. You asked, when was the universe half ionized? And there's a considerable uncertainty here. So we'd like to change that, and we think we can by measuring signals deep in the reionization era. So I'll give you a bit of a tour of what we think, where things stand right now, what the challenges are. I'll be upfront and, of course, say that we have yet to detect the 21 centimeter signal from the reionization epoch. But we are getting close, and the upper limits that we're setting are beginning to say interesting things. Currently, not yet surprising things. It's kind of to be expected, but at least they're starting to say something. I'll talk about some of the challenges, mainly foregrounds and sensitivity. And then I'll also talk about some of the efforts that we're making on the analysis front. And I'll also talk about HERA, our design for HERA, our observational hopes that we hope to achieve with HERA. Okay, so what is the status? What is the current state of the field in terms of high Z 21 centimeter measurements? And I'm going to really breeze through this because I want to get to the future. So there are a number of current instruments that have been making observations trying to measure the signal from, say, redshift 6 through, say, 12. There's PAPA, the precision array for probing the Epoch of Reionization in the South African desert. The MWA, the Murchison Wide Field Array, which is in the Western Australian desert. LOFAR is in the Netherlands, though it does have antennas dotted all across Europe. That is our first non-desert entry. And then we have GMRT here in India that has also placed some constraints. So there are a number of other experiments in addition to these, but these are the ones that have placed upper limits on our signal. And mostly, these instruments have been placing limits on the amplitude of spatial fluctuations that you see, okay? So you see here it's a very inhomogeneous process. You can measure the spatial fluctuations of this on various length scales, essentially for those of you who work on this, the power spectrum. And theory suggests that there are these spatial fluctuations that can be detected that come in at an RMS of about a few millikelvin. Depends on what scale you look at, but that's the fiducial number you should keep in mind. So the observations have collectively put a bunch of upper limits on them, and I can share concrete figures with you afterwards if you want. But roughly speaking, think about it as being about upper limits of about 100 millikelvin or a little less or a little more, depending on which experiment you're talking about. Okay? So what does this mean? We are still a little bit of a ways off, but one of the nice things about studying such an unknown, unexplored epoch is that we know so little about this regime that having fairly weak upper limits still tells you something about the science. So in particular, the current upper limits make it really hard to have an extremely cold intergalactic medium around redshift, say, 8 to 10. Okay? And here's how it works. So imagine you take your instrument out and you're looking at some hydrogen. And suppose that hydrogen is cold. Okay? It's cold. Let's say nothing ever heated it. The only thing it did was hang around and be adiabatically cooled by the expansion of the universe. If that were the case, then with our CMB as a backlight, it turns out the CMB is relatively hot compared to this. And you then end up with a big brightness temperature contrast. That's a very large signal to see. Okay?
You're assuming here that the hydrogen gas just follows the dark matter, just clusters as the dark matter.
Yeah, so it turns out that, in effect, yes. I mean, we do also have models where we are explicitly doing the correlations between the ionization field and the dark matter. But in terms of the intuition for this slide, yeah, just imagine a monatomic gas that's just adiabatically cooling. I'm not even considering the clustering in too much detail yet. So now suppose you now have a warmer gas, okay? You're now going to have a much smaller signal, okay? If the gas had been adiabatically cooled, the signal would be large enough that with current sensitivities, we would have seen this signal, okay? So some mechanism must have heated up the gas, okay? It is, there are a number of plausible mechanisms for that. You can imagine, for example, X-ray emitters like high-mass X-ray binaries or early mini-quasars. And to put some numbers to it, at these redshifts, you're talking about an IgM of about 1 to 2 Kelvin if it were adiabatically cooled. And if you make some assumptions about the neutral fraction, then the gas temperature is at least a few Kelvin above this. Okay? So mostly we do expect there to be some heating, but it's actually unclear. This is already an interesting result because some of the latest models tuning the galaxy prescriptions that go into these 21 centimeter experiments to currently known galaxy populations actually predict some fairly cold scenarios where heating is actually fairly ineffective. It's not usually quite as extreme as saying that the gas is adiabatically cooled, but it's not that far from that. So we're hopeful that in the next couple of years, we will actually be able to improve on these upper limits even before detection and start to say something very interesting. But what are the challenges? Let's air our dirty laundry now, okay? Why haven't we done this already, right? People have been talking about this for admittedly quite some time now. What are the challenges? So the first one, the chief challenge in my view, is astrophysical foreground contaminants. The fact that we are looking for a faint cosmological signal, order millikelvins, whereas we know, for example, that our Milky Way galaxy emits strongly in these low-frequency radio regimes. We're talking, say, 50 to 250 megahertz, okay? And in addition to that, beyond the galaxy, there are also extragalactic sources that also contribute to these radio foregrounds. And these are orders of magnitude brighter. This is a harder problem than, say, with the CMB. Right? With the CMB, especially with today's experiments, if all you wanted to do was see the CMB, point out the galactic plane, and the CMB is basically the dominant signal, at least the temperature measurements. Whereas here, we point out the galactic plane, or choose the cleanest part of the galaxy, and we are still mostly dominated by foregrounds. So we have to do something about that. The typical strategy, and there are variations, but they usually come down to roughly this, is to use the fact that if you take the cosmological signal and you simulate an instrument's observation of this, plot it as a function of frequency, what you find is that the cosmological signal tends to be really rapidly fluctuating as a function of frequency. And the reason for that is because, remember, different observed frequencies map to different redshifts and therefore different line of sight distances. And one distance from me might happen to hit a dense part of the neutral hydrogen and have a very strong signal. Another part might be a less dense part. A third radial distance from me might be in an ionized bubble and have zero signal. So because it's tracing the structure here, you tend to get a very rapidly fluctuating spectrum. On the other hand, foregrounds, we, to leading order, expect them to be fairly smooth functions of frequency. Dominant mechanisms like synchrotron radiation or free-free, which is less important at these wavelengths, but still, mostly, you can parameterize them quite nicely by power laws with slight deviations, and so on. So the hope is, by separating out the smooth versus unsmooth components, we can get a relatively clean measurement of the cosmological signal. And in practice, with current instruments, we're even more conservative than that. Rather than actually doing an explicit subtraction, we just don't look at modes that look like they're rapidly fluctuating. We just make liberal cuts to our data. All the same, it's nice if you can actually understand your enemy a little bit better, right? So far, all I've talked about are the most generic features like smoothness versus unsmoothness as a function of frequency. But it would be nice to actually go in and model some of these contaminants to make sure that our results are robust. The one unfortunate thing is that whereas you go up to frequencies, say hundreds of gigahertz, you've got a lot of great CMB work that has really measured the sky to exquisite precision. At the lower frequencies we're interested in, there's actually not very much data. Okay. So we tried to change that. We're funded by a small NASA grant to just answer the very simple question. Given that we have incomplete observations of the sky at various frequencies, what can we infer about what the sky looks like in all directions and all frequencies? And this is part of a global sky model collaboration where we're trying to answer this in a fairly data-driven way without explicit modeling of the physics. So what we do is you can take a wide selection of survey data, and again, you see it towards the lower frequencies up here, you've got a lot of patchiness, there's just very bad data. You can select the common regions, so these dark brown regions are the most commonly covered areas of the sky. Okay. You can use these common regions to train some spectral templates, essentially some principal component templates that nicely describe the foreground behavior, foreground variations we see in the sky. So here are 3 of these principal components as a function of frequency, for instance. In the latest iterations, we use 6. Find that 6 is required to get a good fit. And then with these, you can basically interpolate as a function of frequency. And so with this, given any frequency of your choice, you can then produce a predicted sky map of what the sky ought to look like despite all these holes. Okay? So this is publicly available software. You just type in your frequency and it returns a map. However, there are some shortcomings to this. And so we've now started working on and actually are about to put out a paper on what we call the extended global sky model. And I do want to highlight the first author here is an undergraduate, very talented undergraduate, Do-Yeon Kim, who's been leading this. She's applying for grad schools right now, and Princeton is her first choice. So if you're on an admissions committee, be nice to her. So problem number 1 is, again, that the low-frequency anchor is lacking, right? I mean, all I've described so far is just a fancy way of interpolating and extrapolating. If you lack an anchor down here, who knows if what you're doing is just, garbage in, garbage out, or if it actually means anything. Luckily, there's been some progress along this front. The LWA, for example, has these really nice high-quality, low-frequency maps now from about 30 to about 80 megahertz. And so we've incorporated that. And so, for example, here is an example prediction that we have in our model for 408 megahertz. So this looks okay, but it is embarrassing in one sense, okay? Which is that when you tell our software, okay, I want the map at 408 megahertz, give me your best prediction, given all the data, it just returns this and says, this is the truth, okay? But we know, obviously, that this isn't really the truth, it's just our model. And typically, these sort of interpolation, extrapolation efforts in the literature haven't contained error bars. Okay? So we'd like to change this. And we decided to do this just by constructing models for the errors in the input data, perturbing our input data, and essentially Monte Carloing through our model to get errors in the final prediction. Now, that's been tricky because, unfortunately, whereas a lot of the CMB data sets come with really rigorously quantified error bars, low-frequency radio astronomers typically do not assign error bars to their work. Okay? So where available, we've used estimates of errors and covariances that have been made available to us, for example, by the LWA. They've got some nice error maps. Where they're not available, we've had to model the errors empirically. And one of the ways you can do this is you can take your collection of input data, and let's say I were interested in modeling the 408 megahertz sky. Okay? So there is a 408 megahertz map, a nice Haslam map here. But what I can do is I can pretend that that data set doesn't exist, run my interpolation, extrapolation model through all the machinery, and that gives me a prediction for what the data ought to have measured. Okay? And from that, what I can do is then I can essentially difference these, and that gives me at least a leading order sense for how good my model is. Some of the errors inherent not only in the survey, but also what's going on here. Now, this isn't really truly the error map, right? There are a bunch of caveats that one needs to put into this. This gives you a bit of a sense for what's going on, and it's a nice consistency check, but it's not really an error model. So we do, in fact, also fit this to an error model. Okay? We have non-SOTs where we basically say, I'm going to assume that in image space, my errors are proportional to these deviations I see here. So where I see larger deviations, I'm going to assume that whether a combination of my instrument or my model, there's larger error bars. But also, there are error correlations that need to be taken into account, so we also model those. We assume that once we've kind of flattened out the position pixel by pixel variations in this map, that the angular power spectrum gives us some sense for the correlations here, and we also go in and explicitly model some of the angular resolution effects as well. So here is an example of our 408 megahertz prediction, and here is an example of one of our error maps. It's quite preliminary, but you do see a lot of the features that you would expect. Some of the features down here, for example, where the errors get particularly bad, those are parts of the map where the input data is particularly poor, basically the northern and southern poles, where we're missing a lot of the data. Okay? And you would expect the errors to blow up, partly because there's less data, our model shouldn't be as good in those regions, and also towards the edge of this, where surveys do cover this region, we expect the errors to kind of ramp up as you're getting towards the edges of surveys. So this will be coming to you soon. There are a bunch of other improvements that come along with this. Talked a little bit about putting some sort of error bars on the output map. Maybe crude, but better than nothing. We also have a bit of a mechanism for figuring out the optimal number of components, spectral components to fit our data to. We're talking about 3 versus 6 components, for example, but you expect the physics of these astrophysical foregrounds to differ in complexity between different parts of the sky, and your parameterization should reflect that. And we also have incorporated more uncertainty in the fact that the 0 level of a lot of these maps are quite uncertain.
You presumably have to worry about the different resolution of the maps at different
We do. So then essentially what we do is you can filter your maps at different spherical harmonic L's, and then use different weightings for the different angular size scales. That's right. And so, for example, at the really high, really fine angular resolution regime, the low frequency maps provide a lot less information than they would at the low coarse angular resolution regime, just because they're coarser. So the end goal is we're putting this all up on Lambda, and the end goal is eventually a publicly hosted, self-updated model of the best guess model of the sky. Given a new map, we want to write ourselves out of the pipeline. That once a new map has passed through our quality assurance checks, we can then go on and just plug it in and have this update all the error bars as well as the map predictions. And one of the nice things about this is we're currently interested in doing this for cosmology, for foreground mitigation, but in principle, of course, just knowing what the sky looks like at low frequencies is potentially very helpful as well. So that's one challenge, and coupled with this foreground challenge, we also have a sensitivity challenge. The fact that our signal is quite faint, especially once you make the cuts you need to get rid of foregrounds. You are now in a regime where a lot of the current generation instruments are barely able to make a detection, if at all. In fact, we would probably place our money on there not being a detection with current generation instruments. So here is a plot of the fluctuation power, power spectrum, against the redshift at a particular length scale. You see curves for the sensitivity of paper, MWA, and LOFAR, and you can basically see we need to be lucky, very lucky, in order for our universe to be kind enough to give us a detection within the purview of these current generation experiments. So to fix this, we wanted to build Hera, right? So Hera is designed to have enough signal to noise to measure the power spectrum to pretty high significance, okay? So the Hera design conceptually isn't that complicated. You take a relatively simple antenna, okay? So we started out with a dipole like this, a sleeved dipole, and we've actually got a new design for the antenna now, and I can show you the design for that afterwards if you're curious, and I can also talk about why we decided to go with a new design. But basically, you take an antenna like this, flip it upside down, use it as a feed for a larger dish, increase your collecting area. So this is now a 14-meter reflector. You hex pack these as closely as you possibly can, okay? And you do that 350 times, and you end up with the hydrogen Epoch of Reionization array, which we are going to place in the South African Karoo Desert. Okay, so this is a fairly large telescope. This is roughly, if you want a mnemonic, it's roughly the size of Arecibo. But of course, with individually digitized and correlated signals from each of these elements. Hera's got a lot of international collaboration. It's order 10-ish institutions that are actively involved. And the design, according to our forecasts, is to be able to constrain the power spectrum to pretty high significance, okay? Conservatively, if we make very conservative foreground cuts, we expect to make kind of 30 sigma detection. If you can play more aggressively with how you treat the foregrounds, we are looking at order 100 sigma detection, at which point the number of sigmas really doesn't matter anymore. So Hera is being constructed right now. This is a picture of the desert. These are the paper antennas, one of the last generation experiments that we just decommissioned. These telephone poles hold up the supports for these dishes. There's Catherine Rosie, our project engineer, doing some surveying work for this. Zakia Lee, one of our grad students, building some of these frames. Here's Karina Cheng, another graduate student. Here's a more complete thing. At these low frequencies, wire mesh is a shiny reflector to radio waves, so it's just a wire mesh screen here. Here's one of our first feeds being hoisted. Here's the hoisting in progress. It's another picture. And this was taken about a year ago when we had, I think, 19 elements on the ground. Okay? And we're now at about 50 elements. And we've started observing, so we're going to do a good season's worth of observing. One of the nice things about building a radio interferometer is that a partially built instrument is still a perfectly fine instrument to be doing commissioning tests on. So, and by 2020, we'll have 350 dishes out there for our first full season worth of observations. And we're funded to build the full thing. Our analysis efforts are funded to analyze about 100 antennas. Okay, so what do we want to do with this? What is the promise? What do we think Hera will be able to tell us about our universe? So again, we would like to measure something like this, distill that down to a power spectrum measurement. And from there, we would like to start constraining parameters. Okay? Can talk, for example, about the minimum virial temperature of these first ionizing galaxies, right? A proxy for the basically the typical mass of these ionizing galaxies. How massive do I need to be to A, not get destroyed, and B, to contribute significantly to the ionizing budget? What is the ionizing efficiency of these first galaxies, right? So how many UV photons do they produce, and how many of those escape out into the IGM from the ISM? What is the mean free path of these ionizing photons? As they travel through the IGM, how far on average do they get to go until they happen to hit a very dense clump of neutral hydrogen somewhere and get absorbed? So here are some example forecasts for these parameters shown in pairwise plots. I should say that even though I just talked about 3 and I'm showing you 3 parameters here, in practice, we've actually now got the machinery to do a lot more than that. worked with a Berkeley grad student here, Nick Kern, to write emulators for computationally expensive simulations of the power spectrum that now allow us to span an 11-dimensional space, including cosmological parameters and some additional astrophysical parameters beyond the ones I just mentioned.
So you're assuming the full set of arrays and observing for n years over.
We are assuming, yeah, so we are assuming the full array, 350 elements, and we are assuming approximately 800 hours of observations, which in terms of real life, you know, in terms of like, okay, well, there's radio frequency interference on this day, we're going to throw out this hour and stuff like that, effectively is about a season's worth of observations. So think a year of observations. Okay, so we think we are going to be able to constrain some of these parameters nicely. I'm going to be the first to admit that this is not the be-all, end-all of reionization science. There are lots of things we will not understand from this. One thing, for example, you notice this degeneracy, just to pick one example, for these two parameters. And we can understand this degeneracy by thinking about moving along the dotted line. If I yank up the virial temperature of these typical ionizing galaxies and basically having reionization be driven by more massive objects, which by construction are rarer, and so what I can do is if I yank up the ionizing efficiency, so each of these objects produces more photons per object, you can basically preserve roughly the overall ionizing budget, and we actually have a bit of a difficult time telling the difference between those scenarios. And this here is something that, you know, what it means is that we will have to complement other observations. You know, it's not to say that other observations are going to be useless once we come online, quite the contrary. But these parameters are not known to, you know, some of these are not known to within an order of magnitude right now. So this would be quite nice progress. And what you can do once you know some of these parameters is then to feed them back into your model and predict as a function of time how these ionized bubbles grew and grew and grew, eventually ionizing the universe, and distill this into that basic quantity I told you about earlier, this neutral fraction as a function of redshift. Okay, so this is the 95% confidence region following the procedure that I just talked about. Okay? So this tells us a little bit about astrophysics of reionization. There's more we can do. We can start asking questions about the nature of these first galaxies. But what I want to turn to next, though, is this idea of whether we can constrain cosmological parameters with 21 centimeter observations at high redshifts. Okay? Because this was one of the selling points originally when this sort of stuff was first proposed. So the basic idea back then was to say, okay, we're probing such a huge volume of the universe, you're going to be measuring lots and lots of modes, and therefore you can beat down your errors very well on a lot of cosmological parameters. That's a nice thing to aspire towards. It's a really nice long-term goal to say I'm going to measure all the modes in the universe. But in the meantime, I think realistically, there's a lot of astrophysics to get through astrophysics as well as instrument systematics. So for now, actually, I think that we can ironically do some better cosmology by doing a little bit better astrophysics. Okay? For instance, we can team up with our CMB friends who generally view reionization as a nuisance. It destroys this nice picture that we provide to popular audiences when we give popular talks of saying that the CMB are these photons free streaming straight to our telescopes. We know in practice that reionization happens, producing free electrons that can rescatter CMB photons, resulting in an extra optical depth parameter that needs to be fit out in CMB data. Okay? Now, this is unfortunate, the fact that there is this extra optical depth parameter, because if you look at the CMB, this here is basically a random field. It's a correlated but random field. So if you take these random hotspots and cold spots, jumble them up by some rescatterings, you're going to average some of them down, and you typically are going to be reducing the amplitude of fluctuations that you observe. This means that you are going to be have a hard time distinguishing between two different scenarios. One where the primordial fluctuations in a universe started out really large amplitude, but then reionization correspondingly happened extremely early, so that you ended up with a lot of this damping and you end up with a small observed amplitude. This is hard to distinguish from a situation where the primordial fluctuations are really small amplitude, but reionization correspondingly happened really late, very few free electrons in a cosmic timeline to do this rescattering, very little of this damping effect, and you get exactly the same observed amplitude. Now, it's true that modern high-precision CMB polarization observations, as well as things like CMB lensing, can really help with this. But what should be clear is that understanding reionization better can help us improve constraints on cosmological parameters. And in particular, Hera will provide us with a slightly more detailed knowledge of the neutral fraction as a function of redshift. If I know this, I can compute the free electron density as a function of redshift. And then basically tell our CMB friends, I think tau is probably this value, so they don't have to marginalize it out of their own data analyses. So to give you a sense of this, here's the CMB degeneracy I talked about earlier. This is actual Planck data, amplitude of primordial fluctuations against optical depth. If we can tell you what the optical depth is, then you break this degeneracy. And in this case, it reduces the error bars on the amplitude of primordial fluctuations by about a factor of 4. Okay? This is potentially also helpful for futuristic CMB experiments, stage 4 experiments, that are trying to do something about a cosmological measurement of the neutrino mass, the sum of the neutrino masses. If you look at structure formation, without neutrinos, you get a lot of very dense structures, very dense, sharp structures. Neutrinos, being light and wispy, don't like to clump into overdensities, free stream out, fuzzing out some small-scale structure. So neutrino masses typically damp out small-scale power in the density field, which means that you have an observational degeneracy. You've got two effects, one where the neutrino mass can actually change the amounts of small-scale structure, and the optical depth not actually changing the amounts of small-scale structure, but changing the amounts of small-scale structure you see in the CMB. And this can lead to an observational degeneracy. So here's an example forecast plot for next generation CMB experiments, some of the neutrino masses against the optical depth. If I know the optical depth, I can help the situation a little bit, slightly tighten up the error bar, predicted error bars on some of the neutrino masses. Now, one very reasonable objection to this is that isn't this awfully model dependent, right? You're talking about reionization, presumably a fairly icky, messy astrophysical thing. I had to model astrophysical parameters on my way to getting this prediction of optical depth. Isn't this model dependent? Yes, it is model dependent, but it's still worth a try. And there are some things that I think help mitigate the situation a little bit. So for example, if you look at a typical reionization signal, for a 21 centimeter signal, reionization, the large-scale structure of reionization tends to be driven by the density field, right? The density field is the primary input, for example, into a lot of semi-numerical codes. And you see here what we call inside-out reionization, densest parts of the universe reionizing first. So one of the crucial ingredients of an analytic prediction for this sort of measurement is the correlation between the ionization field and the density field. So one can actually look at some variations in model dependence by playing around with this correlation. You can imagine, for example, taking one of these simulations and as a very extreme model, extreme example of a model variation, just flip the sign of these correlations. That's a fairly extreme change, right? But was keeping all the detailed astrophysical parameters the same as far as you can, okay? So if you do that, of all the things that came up nicely on this projector, this did not. If you look carefully, there's a gray bar here, and that is what you get. That's how much the constraints fuzz out if you go to these rather extreme variations, where I'm literally flipping the sign of correlations between density and ionization. So this, while not the final word on how precise our models can be, I'm not going to guarantee anything until we actually made the observations, gives you a sense for, it gives you a bracketing. This is the sorts of model variation you might expect, widening things up to here, but still potentially interesting. Another way to alleviate model dependence is to use other algorithms as well to try to better understand our systematics. And so one of the things you can do is to say, okay, what you've done so far is to take observations, converted them into a power spectrum where you have good signal to noise, converted that into model parameters, fed those back into a model to give you a theory prediction for the ionization history and therefore the optical depth. Well, that is in some sense kind of wasteful, right? It's very indirect. There are also a lot of non-Gaussian features in these sorts of fluctuations that are not captured by the power spectrum statistic. So one thing you can do is what we've experimented with is to try to use machine learning to try to directly go from some of these observations to a prediction for tau. We've been experimenting with what's called a convolutional neural network, where you basically take some of these observations. So now we're not talking about power spectrum, we're talking about some imaging data where you actually made pictures. You then basically take this picture, put it through a series of convolutions. So basically you have a bunch of convolution kernels that sweep through this input picture, picking out various important features, have a whole bunch of them. You then threshold this measurement to say that only features that appear at a certain strength get picked up, okay? And then you basically repeat the process. You do a whole bunch of other more convolutions. You keep going, you keep going, you keep going. At some point, you might also average things down a little bit to reduce the data volume. And then finally, you have a bunch of what amounts to a bunch of numbers extracted that quantify various features that have been picked up by this network, and you form a linear combination of them to form this prediction for tau. And the way you know how to do this is you basically take some training data where you've simulated a whole bunch of universes where you know what the correct tau is, where you vary all sorts of messy astrophysics, anything that might affect your measurement, including instrument systematics. So we've included that. We blur out things. We make cuts in the data. And you basically repeatedly expose these training data to this network, which initially gives you tau values that are just complete nonsense. And from there, you then basically do gradient descent to adjust the parameters of the convolutional kernels until you better match the actual value of tau you know from simulations. And that way you can train this network to pick up on exactly the right features it needs to make this determination. So here are some preliminary data. These taus are in arbitrary units. So the best fit Planck value of tau would be somewhere here. These are arbitrarily scaled. So this is the true tau that I know from simulations versus the recovered tau from putting a mock observation through my convolutional neural network. And typically for this, you see I've not only tested this on the training data that was used to train the network, but also on some test data that was kept separate that is only used for this final test. And you can, in fact, recover tau to a few percent. Okay? Now, in principle, this isn't all that you can do with it. Right? I talked about how a lot of the maps that we see are driven by large-scale structure. Right? The fine details may be driven by astrophysics, but the broad brush features are driven by large-scale structure. And therefore, in principle, hiding underneath all of these complicated observations is just a matter of distribution. So you can also train a neural network to try to recover the matter power spectrum. And this is so preliminary, I'm not even going to show a plot, but tentatively we do think we might be able to train a neural network to be able to do stuff like that. You won't ever get it perfectly because ultimately the details of astrophysics are going to matter, but coarsely you might at least, to a factor of few, be able to constrain something about the matter distribution at these high redshifts. So just to wrap up now, some take-home messages. We have not yet detected the high redshift 21 centimeter signal, but we are getting closer. Upper limits are getting better year by year. And we think, we've already gotten to the regime where we're starting to push on some more extreme models, and very soon I think we're going to be able to push on some more less extreme models as well as to get our first detection. The main challenges are foregrounds and sensitivity, and we are working hard to improve our analysis efforts, both on foreground models and machine learning, but also a whole bunch of other stuff that I haven't talked about, how to better estimate our systematics, how to actually do precise cuts on our foregrounds and our data, and so on. And we're very excited now that Hera is being constructed and is actually taking data as we speak. So hopefully that will lead us to a first detection within the next 3 or 4 years, and beyond that, some of these nice constraints that I highlighted just now. Thank you very much.